Hello friends, welcome to this video. So in this video we will learn some basics of what is microprocessor and controller organization. So in this video we will mainly focus on two topics, that is what is instruction code and what is addressing modes. First of all we will see what is instruction code. So an instruction code is a group of bits that instruct the computer to perform a specific operation. So for example, the programmer writes the program. And first of all, what is the program? So program is the set of instructions which contains the operands, operations, and the sequence in which instructions should be executed. So like that way, when a programmer writes a program, that will converted into assembly language, and then that assembly language will be converted into machine code. So that machine code will be the group of bits which instruct the computer to perform a specific operation on the operands which programmer has written. So now how this instruction code looks like and how this instruction code stored in a memory, we will see that. So we have understood that what is instruction code. Now we will see that how instruction code looks like. As I said, instruction code is a group of bits. Here I have taken instruction of 16 bits, that is 0 to 15. So this will be the group of bits only. The instruction code is mainly divided into three parts, that is the operation code, address, and addressing mode. So first of all, what is operation code, or we can say opcode? So opcode represent that which operation should be done on operand. So for example, here I have taken the operation code of 4 bits, that is 15 to 12. But it is not necessary that in all microprocessors the operation code will be of 4 bit only. It may be different on the basis of microprocessor design. So if a microprocessor can perform 64 operations, then I will require 6 bits to represent 64 different operations. So how we can come to know that how many bits we will require for the different operations? So here I have done that 2 raised to 6 will be equal to 64. So with 6 bits we can refer to different 64 operations. If we also have 60 operations, then also we will require 6 bits. So in this way we can conclude that how many bits we will require for the operation code. So now what is this address part? So it will store the information related to operand, and in the way it stores the information about operand is known as addressing mode. The addressing mode part we will discuss later on in detail. So now how we decided that the address will be of 12 bits. So on the basis of the size of physical memory, so for example here we have take 4096 by 16. It means there are total 4096 different registers, each of 16 bit. Here in this memory it is divided into two parts, that is the program memory and data memory. In program memory the instruction will be stored, and in the data memory operand will be stored in binary form. So when we divide this physical memory into two parts, we called it von Neumann architecture. And when the instructions are stored in different memory and data is stored in different memory, then that architecture is known as Harvard architecture. But we will not go in depth in that architectures, von Neumann and Harvard, but we will see that how this 12 bits address is decided. So to refer 4096 different addresses, we want 12 bits, because 2 raised to 12 will be 4096. So to refer different 4096 addresses, we will require 12 bits. So here we have taken 12 bits of address and remaining 4 bits of opcode. So depending on the size of memory, the address bits can also be changed, and the basis of number of operations a microprocessor can perform, the number of opcode bits can also be changed. And in the data memory, we will store this operand, and as each register is of 16 bit and operand is not divided in further parts, so the whole 16 bits 0 to 15 will store the data, that is the operand. So here we have understand the format of instruction and in how many parts the instruction code is divided. So now we will move on to our next topic, that is addressing mode. So as I said that the different ways of specifying the location of an operand in an instruction is known as addressing mode. So before starting the addressing mode, we will see a term that is known as effective address. So what is effective address? It is the address in the data memory where operand is stored. So for example, let's say our operand is 70 and it is stored in the data memory at an location, let's say 1010 0011 1101. So it is the 12-bit address in the of the data memory where 70 is stored. So 70 is our operand, and its address, we will say it that if it is the effective address. So now we will start the types of addressing mode. So in total there are 12 types of addressing mode which I have listed here, but out of this 12, today in this video we will see only 3 basic types of addressing mode, that are immediate addressing mode, direct addressing mode and indirect addressing mode. So first of all we will see that what is immediate addressing mode. So now what is immediate addressing mode? So sometimes it is more convenient to store the operand directly in this address field. So rather than storing the address of an operand, that is the effective address, we will direct store the operand in this address field. So when we directly stores the operand in instruction, then it will be immediate addressing mode. So now the another 2 types of addressing modes are direct addressing mode and indirect addressing mode. So in these both modes we are storing the address in this field. In immediate addressing mode we have stored operand, but in this both addressing modes we will store address here in this 12 bits. So if you see, I have changed the instruction format. Initially when we have seen the instruction format, there are only 2 fields, that is the opcode and address. But now I have added one more field, that is ith bit. So I have made that 15th bit, that is the ith bit, will represent the addressing mode, that this instruction is of which addressing mode, direct addressing mode or indirect addressing mode. And we have made the opcode of 3 bit, 14, 13 and 12 rather than 4 bit. So this change we have done in the instruction. So we have said that when the ith bit is 0, at that time the addressing mode will be direct addressing mode, and when the ith bit is 1, at that time addressing mode will be indirect addressing mode. So now we will see that what is direct addressing mode. So here example is given that in the memory this instruction is stored, that is at the address 22. So here ith bit is 0, the opcode will be in binary, but here we have written in assembly level language, that is add. That here for example for add operation the opcode is 010, this 3 bits 14 to 12, then it will do the addition operation on the operand which is at address 457 with the content of the accumulator. So here in the memory this instruction is at 22 address, and ith bit is 0, which represent the direct addressing mode, and the operation is add. So in the direct addressing mode the address is given of the operand. So here 457 is given, so this will be the address of the operand stored in the data memory, and this instruction will be stored in program memory. So when this instruction is decoded, at that time by seeing this 0 bit the computer comes to know that this is the direct addressing mode, and it will decode the address such a way that at the 457th location in the data memory it will fetch the operand and perform the operation on it. So now we have understood the concept of the direct addressing mode. So now we will move on to what is indirect addressing mode. So here in direct addressing mode, in the address field of instruction we will direct providing the effective address, but in the indirect addressing mode, in the address field of the instruction we will not directly provide the effective address, but rather we will provide the address where the effective address is being stored. So for example in the memory at the address 35 location in the program memory there is an instruction stored in which the ith bit is 1, and the ith bit is 1 represents that it is an indirect addressing mode. So when the computer decodes this instruction and sees that ith bit is 1, it comes to know that in the address field this address is not the effective address. So when computer knows that this is not an effective address, it will goes to this address, that is 300, and it sees that at 300 the effective address is stored. So it will fetch first effective address, and from effective address it will fetch the operand. So in this way, in indirect addressing mode, operand is fetched where in the address field effective address is not given, but rather the address where the effective address is stored will be given in the instruction. And here as we seen in the direct addressing mode, this is the opcode of 3 bit which represents that what operation should be done on this operand and the content of accumulator. So I have used the word accumulator. So what is this accumulator? So accumulator is the register in the ALU, that is arithmetic and logic unit. So in the ALU there will be a register whose size will be same as our physical memory size. In the physical memory which we have seen, that is of 4096 by 16. So here there are 4096 different locations where each register of 16 bit will be there. So here from the memory size we came to know that each register will be of 16 bit. So accumulator will be of same size, that is 16 bit. So 0 to 15 in the ALU. So what is the use of this accumulator register? So accumulator register is used to store the operands as well as the results, that is after performing the operations. So when we want to perform addition operation, let's say 5 plus 17, then first of all we have to store this first operand in the accumulator. So this operand is fetched from the data memory and stored in the accumulator in the ALU, and then the instruction which is having the here ith bit as the addressing mode, then opcode will be add because we want to perform addition operation, and the effective address, for example let's say that instruction is having direct addressing mode, so ith bit will be 0, we want to perform addition, so opcode will contain add, and address field will contain the effective address of the second operand, that is 17. So in the data memory where 17 is stored, that address will be in this instruction. So for example 17 is stored at address 457, then this will be the instruction. So what after executing this instruction, what ALU will do, that it will perform the addition operation of the content at 457th address in the data memory with the content of accumulator register, and again this result is stored in the accumulator register only. So this is the use of accumulator register. So some of you will say that why we don't only fetch the operands from data memory and perform the operation on it. So all the operations which can be arithmetic or logical are performed in the ALU, that is the arithmetical logical unit, and it will be in the control unit. So if we want to perform any operation on the operands, so first of all it will be fetched from the data memory, and that it must be temporarily stored somewhere in the ALU. So for storing the operand for the temporary purpose, we will have registers in the ALU. So one register that we discussed, that's the accumulator, but other than that there are many different registers for different purposes. So all the registers in the ALU will have different purpose and store different types of data. So in this way temporarily data will be stored in the ALU and the operation will be done on that data or operand, and the result will be stored in the accumulator. So that's it for today.